Sketch a function that is fifth degree with zeros only at 2, -5, and 0. I'm going to start by putting my zeros on my x-axis, -5, 0, and 2. So being that it's a fifth degree, we know something about odd degree polynomials. They have to start going one way, say, have their arrow pointing up at the beginning, and then have their arrow pointing down at the end. So they have to alternate the arrows or vice versa. Now, if I were to just draw and start with my arrow pointing up at the beginning, so it'll be like this, and go down, hit through, and then just make a curve like this, that's fine. The arrows follow the rules for odd exponents ending in the opposite direction for our end behavior. However, we need it to be a fifth degree, and there's only 3 zeros. So if I were to start writing the equation for it, I'd have x plus 5, x, because it's 0. Remember, the plus 5 goes with this -5 intercept. The 0 goes with the 0 intercept. And then the plus 2 would be x minus 2. If you look at how many x's, or what I would have if I added the exponents, I'd only be x to the third. These have to have an extra degree added in a couple places. So we have the choice, and this is where your equation could differ from mine, but I'm just going to go ahead and put a squared power on this 0 and a squared power on this 0. Again, those are random. I'm just going to change and make it that way. So what I'm going to do here, erase my polynomial. Okay. Whenever I have a double 0, remember we call it a double root or a double 0, it doesn't cross through the x-axis. It actually just bounces off. So if I come down here, I'm going to start with my arrow up. I come down to the -5 intercept. I'm going to bounce off that because I've created this double 0. That means it turns around. It doesn't go through to make an extra 0. Then I'll come back up, and I'll have to turn around here, and then now I'm going to go through 0 because it's not a double 0. Then I'll come back up, and I'll hit my 2, but I'll bounce back off, if you will, because it's a double root or a double 0. Now, look how many bubbles or local maxes and mins I have. 1, 2, 3, 4. Again, that should hit that there. That makes a lot of sense being a fifth degree, because fifth degrees could have 4 or 2 or 0 local maxes or mins. So this would be one possible sketch for a function that has the end behaviors to match and the zeros, but it also has a couple double zeros in order to reach the fifth degree. Now do keep in mind, our beginning here is pointing up when we start. It's pointing up on this end behavior, but it's pointing down on this end behavior. We need to watch how that very final end behavior is, and this is going to help us indicate if we need a positive or a negative out front here. Because the final, or the very ending end behavior, if you will, is negative, we need to have a negative sign thrown in the beginning of our equation. Now, it never said to write an equation, but I wanted to redo this because this is kind of a tricky part of writing the equations, checking how many zeros you have, and matching the degree. This negative, again, is because our final end behavior is going down to the bottom. Just like if I would make an x squared parabola and it goes like this, the reason that final end behavior is up is because that's positive. If it was a negative x squared, it would be a parabola going down, and that very end behavior right here is negative. It's always about the final arrow, not so much the first arrow, that helps you indicate whether you need a positive or negative in front of your polynomial equation.